Why is detecting the structural characteristics of active electrode materials important for the development of high-performance, long-life, and low-cost sodium-ion batteries? And how do these characteristics impact the overall efficiency and longevity of the batteries? What are the key structural characteristics of electrode materials that need to be analyzed to optimize battery performance, and how do factors such as crystal structure, microscopic morphology, specific surface area, and pore size distribution of particles play a role in determining the performance of sodium-ion batteries? How do the valence and element distribution of electrode materials influence their electrochemical properties, and why is understanding these factors critical for improving the efficiency and capacity of sodium-ion batteries? What role does thermal stability play in the performance of electrode materials, and how does the ability to withstand temperature variations contribute to the overall safety and effectiveness of sodium-ion batteries in real-world applications? How do these various structural characteristics of materials combine to determine the suitability of electrode materials for sodium-ion batteries, and in what ways do they need to be optimized to achieve the desired balance between cost, longevity, and performance? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? What are the mechanical properties of active electrode materials for sodium-ion batteries, and why is it important to understand these properties when designing batteries? How does the valence bonding coordination structure of electrode materials affect their electrochemical performance, and why is this structural aspect critical for the overall efficiency of sodium-ion batteries? What are the various characterization techniques available for analyzing the mechanical properties of active electrode materials, and how do these techniques help in understanding the material's strength and flexibility? In what ways can different characterization methods be applied to determine the valence bonding coordination structure of electrode materials, and how does this influence the battery's capacity and stability? Why is it necessary to introduce multiple characterization techniques when studying active electrode materials, and how does each technique contribute to a comprehensive understanding of material behavior in sodium-ion batteries? How do these different techniques complement each other to provide a complete picture of the material's performance under various operating conditions, and what role do they play in optimizing the material for better cycling stability, efficiency, and lifespan? How does the use of these techniques help improve the design and functionality of sodium-ion batteries, and what are some examples of how these methods have led to breakthroughs in material development?